You know, when we think about what makes an engine work, we usually picture the big stuff, right? The pistons, the combustion, all that power. But deep inside, there's this hidden component, kind of like a mechanical brain, that keeps the whole show running smoothly. So today, we're going to pull back the curtain on this unsung hero, the engine governor. So let's start with a basic question. Picture this, you're using cruise control, and you start heading up a steep hill. The car doesn't just slow to a crawl, does it? Nope. Something tells the engine it needs more gas to keep the same speed. Or think even bigger, like a massive power plant generator. What happens when millions of people suddenly turn on their TVs at the same time? What stops that huge turbine from just bogging down? Well, the answer to all of that is the governor.
Now, you might be thinking, hold on, isn't that what a flywheel is for? And that's a great thought, but they actually have totally different jobs. The best way to think about it is like riding a bicycle. The flywheel, that's your bike's momentum. It's what keeps the wheels turning smoothly between each push of the pedal. But the governor, that's your brain. It's what sees that big hill up ahead, that's the increased load, and makes the conscious decision to tell your legs, okay, time to pedal harder. One smooths out the tiny bumps in the ride, the other manages the entire trip.
So, how do these little mechanical brains actually think? Well, they really come in two main flavors, and the biggest difference between them is what they're paying attention to. Are they just reacting to the speed you're at right now, or are they reacting to the change in speed? It sounds like a small difference, but it leads to two completely different ways of doing things. First up, you've got the centrifugal governor. Think of this one as the reactive type. It actually feels the engine speed drop, and then it kicks into action. It's kind of like you're on that bike and you only start pedaling harder once you notice you're already slowing down on the hill. But then you've got the inertia governor. Oh, this one's the clever one. It's predictive. It doesn't wait for the speed to actually change, it senses the rate of change. That split second the engine starts to slow down. And because of that, its response time is way faster.
All right, that's all the theory, but to really get it, you gotta see how they're built. So let's pop the hood and take a look at two classic centrifugal designs. This is where you can literally see the physics doing its thing.
First, we have the Porter Governor. Its secret weapon is just beautiful in its simplicity, a big, heavy weight. Just imagine this central load sitting on a sleeve, connected to these arms that are spinning around with balls on the end. The whole thing is just a perfect dance of physical forces. And the physics behind it creates this amazing self-regulating loop. As the engine spins faster and faster, those balls fly outward due to centrifugal force, which physically lifts that heavy central weight. That simple up and down movement is hooked right into the fuel supply. Speed goes up, the sleeve lifts, and it closes the throttle just a tiny bit. Speed drops, the sleeve falls, and it opens it back up. It's a perfect mechanical feedback system.
But, relying on a big, clunky weight isn't always the best or most efficient solution. So what's the modern take? Well, that's where the Hartnell Governor comes in. It does away with that bulky central load and replaces it with the precise, engineered resistance of a spring. It's like old-school gravity going up against modern precision engineering.
And just like with the Porter, the engineering here is all about finding the perfect balance. The whole game is to pick a spring with the exact right stiffness. It's got to be strong enough to fight back against the force of those spinning balls, but also sensitive enough to compress and expand with incredible precision. That's how it keeps the engine's speed locked in, no matter what you throw at it. Okay, so we've seen how they work, but how do we know if a governor is actually any good? How do engineers tell one from another? Well, they've got a few key stats they look at, almost like a performance review for a machine. First on the list is stability. And a stable governor is, above all, predictable. It simply means that for any single speed, those spinning arms will be in one, and only one, very specific position. There's no wiggle room, no guessing. It's just a consistent, reliable response every single time. Next up is something called sensitiveness. And yeah, it's pretty much what it sounds like. How alert is this thing? A really sensitive governor can pick up on the absolute tiniest fluctuations in speed and react immediately. It's the difference between a system that waits for a huge problem and one that fixes a tiny issue before it even becomes one. And then there's the holy grail, isochronism. This is really a theoretical ideal, the idea that a governor could be so perfect that it holds the exact same speed no matter what load you put on it. In the real world, it's pretty much impossible to achieve without causing other problems, but it's that perfect bullseye that all engineers are aiming for.
So this brings up a really interesting paradox. We want a sensitive governor, right? I mean, that sounds like a good thing. But is it possible for it to be too sensitive? What actually happens when a system is maybe a little too good at its job?
Well, you get a condition that engineers call hunting. And this is what happens when a super-sensitive governor basically panics. It senses a tiny dip in speed and throws the fuel valve wide open. Whoosh! The engine screams past the target speed. The governor panics again and slams the valve shut. The speed then plummets. It just gets trapped in this endless cycle of overcorrection, constantly hunting for the right speed but never ever finding it.
So we've gone through the theory, the mechanics, the good and the bad. Let's bring this all back to the real world. Where are these hidden brains actually working around us, day in and day out? I think the answer is going to surprise you.
The truth is, they are literally everywhere. That cruise control that makes a long road trip so much easier, that's a governor. Those mind-bogglingly huge turbines in a power plant that have to provide steady, reliable electricity to millions of homes, all managed by governors. From the incredibly precise speeds of industrial lathes and drills, to a massive ship's engine crossing the ocean, even to the elevator you might have ridden this morning, all of them depend on this unsung hero to keep a perfect, stable speed. So you see, the governor is way more than just a clever piece of mechanics. It's a perfect example of a quiet, self-regulating system that really does make our modern world possible. And it kind of leaves you with this thought, doesn't it? What other invisible mechanisms are out there, silently correcting and adjusting everything?